So we started 1.5 last time, took a look at some information in this section, and we got to the point where we had talked about and found one slant asymptote, right? And I think that's where we stopped. It was at this example. Does that sound right to you guys? Okay, so let's take a look then at Theorem 5.1. Theorem 5.1 says that if you have any rational number t greater than 0, so it doesn't have to be a whole number, it just has to be a positive number. So if you have a rational number bigger than 0, so it could be a fraction or a decimal even in other words, and it's the exponent on the bottom of the x, right? So 1 over x, you've got an exponent on x of this rational number, that this limit is actually 0. And when x is approaching negative infinity, we assume that the t is equal to some rational constant where the q is odd. And that just has to do with finding, if we were talking about, for instance, like a square root on bottom, which would be an exponent of 1/2. So like if we had this, which is equivalent to this, that wouldn't work as x goes to negative infinity because we can't have negatives underneath a square root. So that's all this last part's talking about, is that we're only going to do rational exponents with the denominator being a odd number if we're going to talk about going to negative infinity. Okay, so it's just sort of saying we're not including the ones that don't exist. That's all that statement's saying. And then it talks about polynomials. So you've seen this definition before, I'm quite certain. You probably tried to ignore it when you saw it because it looks very strange. All this definition says is that you have exponents on x that are whole numbers, okay? That's what it means for it to be a polynomial. So we've got 2s or 3s or 59s or something like that. They're whole number exponents. And these a sub n's in front are just coefficients, so any numbers in front. So maybe this looks like something like 3x to the 5th minus 4x plus 2. It's just a polynomial, okay? What this is telling you is that if the n value, the a sub n at the beginning is greater than 0, that this is going to go to infinity. And if the a sub n at the beginning is less than 0, it goes to negative infinity. And we'll just use a couple of examples that you're very familiar with to talk about that. Let's just say we talked about x squared. Well, x squared, that 2 I'm sorry, the number in front of here is what I was talking about. Let's do 2x squared. So the number 2 in front of here is a positive number. And if you take a look, the graph looks something like this. So if you trace along this graph as you go to infinity, that is positive infinity, you trace along the graph like this, right? And this graph goes to infinity. So the positive exponent in front is actually making this graph be infinity. And if that had been a negative exponent in front, like negative 2x squared, the graph instead would have opened downward. Whoops. And as you moved to the right towards positive infinity forever, instead of the graph going up forever, it would be going down forever. So all this is telling you is that the coefficient at the very beginning tells you whether the graph continues on upward or whether it continues downward. And there's nothing special about x squared. I just used a graph you're familiar with. So it could be any power at the beginning of x, and it wouldn't make any difference. So on this one, what would the limit be as x goes to infinity? Positive, because it's a positive coefficient, right? And that's all it's saying. So if we looked at this limit as x goes to infinity, it would also be positive infinity. And again, because on the end it's going to go upward. Yes?
So kind of a question in relation to polynomials on continuity. Those kind of polynomial functions are continuous on all intervals.
Yeah, any polynomial function is going to be continuous on all intervals, so negative infinity to infinity. That is a feature of polynomials and sine and cosine. And it's a feature of square roots and cube roots, also those powers.
Sine and cosine are continuous on all.
Sine and cosine are. Now, tangent and cotangent aren't, so we can't just say trig functions. We can say polynomials because it really works for all polynomials, but the only trig functions for which that's true is sine and cosine. All the others have asymptotes, so yeah. Any other questions on this idea at the moment? Okay, let's try a couple of examples. So this one isn't a polynomial, I understand that, but it does have pieces of which that are. This one asks us to determine each limit, answer is appropriate, with a number infinity or negative infinity, or doesn't exist if that happens. And the limit actually is talking about the limit as x goes to infinity of 2x squared minus x plus 1 over 4x squared minus 3x minus 1. Now, we encountered functions like this in the last time when we talked about in this section. We encountered them way over here when we were talking about asymptotes. Okay? We talked about finding vertical and horizontal asymptotes. Yes?
On my paper, it's exclamation marks. Was that on purpose? Is that on purpose?
I have a feeling that whatever you used to open it didn't like things. So just rewrite it in. And I don't know how that happens because I save them as PDFs, so they should be just pictures, but every now and then somebody gets gobbledygook when things print out. So no, it shouldn't look like that, Tammy. All right, so just write in, oh, and I moved the screen. Let me move it back. Write in this particular function. Okay, so this is a rational function, right? Rational functions have asymptotes, typically speaking. We get vertical asymptotes when the denominator equals 0. That's what we talked about last time. And then we get horizontal asymptotes by looking, or we figure out what they are, by looking at the degree of the numerator and the denominator and comparing. Everybody remember that? Now, looking at horizontal asymptotes is the same as looking at limits. For example, and this isn't the image of this particular graph, but let me just draw one so you can see. Let's say, for instance, you had this particular graph. So those are asymptotes, obviously, that I've drawn in. And the graph looked like this. And let's say that the height right now, right there, is 3, okay? So the height that we're at there is 3. Then the horizontal asymptote, obviously, is y equal 3. Agreed? Well, that's also the limit value as you go to the right forever, because you're getting close to the y value of 3. And it's the limit as you go to the left forever, because you're going close to the limit value, or the y value of 3 on the left side of the graph. So as you go to positive infinity and to negative infinity, you approach the ends of the horizontal asymptote. Make sense? So when we're asked to find a limit for a rational function, it's equivalent to being asked to find the horizontal asymptote. Okay? I'm going to write that here so that you will write it as well, because otherwise you're just going to stare at me, I can tell. We need to find, and I'll abbreviate, the horizontal asymptote. If we can find the horizontal asymptote, we likewise find the limit. So the horizontal asymptote, which will be our limit as x goes to, and actually it's positive or negative infinity. We're only going to do it positive infinity because that's all we're asked for right here, right? But this actually would work if it said negative infinity as well. So take a look. Yes, do you have a question first?
Just by like looking at it, that it's not a what's the word, sideways asymptote or something?
It's a good question. So we're gonna hit that right now. So the question is, how do we know if this has a horizontal asymptote at all first? What is it that we look at? Not coefficient. Exponent. We want the exponent. So the highest exponent, in fact, right on the top and on the bottom. So these two highest exponents, we call that the degree, are the same. So far, so good? Okay, so the degrees are the same. So if we come back over here, which case are we in if the degrees are the same?
3.
3. We're in case 3, which then we look at the coefficients, like you said, right? So what do we see when we look at the coefficients on these two highest degree terms?
1/2.
We get 1/2. So what that actually tells us is that my limit is 1/2. Because this, y equal to 1/2, is my horizontal asymptote. Okay, I'm going to take this picture away because it's not supposed to go with this particular graph. I was just explaining from a generic point of view. Okay, so my horizontal asymptote is 1/2, which means that I actually have 1/2 as my limit as well. Now, to answer the question you asked, how do I know if there's a slant asymptote? Slant asymptotes happen when the degree of the numerator is exactly 1 bigger than the denominator. So on this one, if the degree on top had been a 3 instead of a 2, I'd have a slant asymptote. And if I have a slant asymptote, that means the graph either goes to infinity or negative infinity, because it actually doesn't level out like a horizontal asymptote does. So that's how I'll know, is I still look at the degrees of the exponents. Let's try another one.
That was it?
That's it, right? It says, determine each limit with a number, infinity, negative infinity, so a number is what we actually found on this one, a number, or the value infinity, or the value negative infinity, or the value does not exist. And this one was a number, 1/2. It's not too bad, right?
Okay, just.
And that one's not. What's that?
First thing I did was just factor it and cancel, but that's not really good.
You can factor and cancel, and it doesn't hurt anything, but it's not necessary for the question asked for this question. Right? So if we were to factor, the reason we would want to do that is to find out where we have vertical asymptotes. And we weren't asked about vertical asymptotes in this particular equation. Does that make sense? Now, you could be asked to find vertical asymptotes, horizontal asymptotes, and limits all in the same question, in which case you would still need to do the factoring. But the factoring is only necessary if you're finding vertical asymptotes, or if you're trying to reduce something to find out holes in the graph potentially as well. But we weren't asked for either of those on this particular question.
So when you're trying to find the limit, you're only looking for a horizontal asymptote?
Exactly. A limit is horizontal asymptotes. And let me clarify that. A limit is you go to infinity or negative infinity.
Okay, that's what was.
That's what's going on, yes. This limit is a limit at infinity. Okay, so infinity means the edges of the graphs, okay? So if you're finding a limit at a function, like at an actual value like 3, then yes, we need a factor. That's different. But we're finding limits at infinity. That's what this chapter, this section in this chapter is about, is limits at infinity. Does that clarify a little bit? So finding limits at infinity is talking about horizontal asymptotes. Yes. All right, this is another one. Same direction. Again, the limit says at infinity. But this one looks a little bit different because of what?
There's a rabbit.
There's a square root in the denominator, right? Okay. Now, some of you don't like square roots in denominators because somebody in trig or otherwise told you you can't leave square roots in the denominator, right? And that's a true statement if the square root is a value that's a number. Right now, I've got a variable in the denominator, x. So depending on x and what x actually equals actually depends on whether or not that square root ends up being a whole number or not. Agreed? So for instance, if that x value underneath there is a 3, is 3 going to do it? I think so. The x value, no, it won't. I was thinking about 4 squared. Depending on what that x value is, however, will depend on whether or not I add the 4 to it and I actually get a square root that I can take. So there's no need to just rationalize things that have variables in them because we don't know whether or not they're rational or not. So we're not going to rationalize. That's not the approach we want to do. But we're going to still consider the largest exponent, okay? So we did the largest exponent in the last one. It was truly a rational function, though, correct? I mean, like I have something that's for sure rational on the top, it's a polynomial. For sure rational on the bottom, it's a polynomial. This one, I've got a square root in it. So it's not really a rational function. However, it does still have the same limiting behaviors. I still look at the highest degree. So for instance, on top, the highest degree, of course, is 1. On bottom, the highest degree is 2. But it's underneath a square root. Agreed? So this function is approximately equal, let me say it this way. This function, not with the limit part of it, but the function itself is approximately equal to this function. That's not a good 2. That 4 plus in the denominator does not affect the end behavior of the graph. Much like the x here, the 3x, the 1s, they don't affect the end behavior. They don't affect what happens on the ends of the graph. Because as x gets very, very large, the x squared here gets larger faster than the other pieces. That's what's really happening. The bigger power is the one that's dominating what's happening. Okay? So it's kind of like the expression that you say that the squeaky wheel is the one that gets oiled, right? The one that's causing the most problems is usually the one that gets the most attention. The same thing's true with our mathematical equations. The one that's going to be the biggest value is the one that's going to determine the ends of the graph, the end behavior. So on this one, these two functions are approximately equal. And in fact, their limits are equal. So when I'm finding this limit, this is going to be equal to the limit as x goes to infinity of negative x over the square root of x squared. Okay? The functions are not equal, but the limits will be, because that 4 plus does not affect the limiting behavior. But what's the square root of x squared? Yes, it is. So what happens now? This is negative 1. So the limiting behavior, the asymptote, and it is an asymptote, it's a horizontal asymptote that you get close to on the end of the graph as you go to infinity, is going to be negative 1. Now, it's worth noting here that this is going from x goes to positive infinity, I could use the x going to negative infinity, but I would get a different result. Okay, so this is x going to positive infinity, so I'm going to the right forever.
So in that case, if
What
we
case?
even, in this, compared to number 3, number
Yes.
4, we didn't even really need to use the, degree theorem.
Well, we used the degree because I considered only the highest degree on top and the highest degree on bottom. So let's say, for instance, the highest degree on the bottom said x to the 4th. Okay? So if I had the x on top and the x to the 4th on bottom, I would actually end up getting a higher degree on bottom than the top. So we simplified this and recognized that this x is sort of canceled out, but it would also be equivalent if we looked at the coefficients of each of those x's. It just didn't happen because they were the same on this one that we looked at. Okay, I think there's one more, right? All right, this one's different because of what? The sine. And sine has this behavior where it just goes up and down, right? It's a wave. So it's different. Definitely different than polynomials, that they don't do that. They don't go up and down indefinitely. Let me say it that way. So the one thing that we do want to know, though, is that while sine goes up and down, there is a highest value that it goes to and a lowest value. What are they? 1 and negative 1. So sine values don't get any higher than the y value of 1, no matter what the x value is, and they don't get any lower than the y value of negative 1. So they're sort of trapped, right? They're trapped between those two values. So the first thing I want to write down is that feature, because that's going to affect what's going on in our answer. So sine of x is bounded in this way. Negative 1 is less than or equal to the sine of x is less than or equal to 1. So what that tells us is that while it goes up and down, it bounces up and down forever, that the other two features on the graph, the x squareds right here, are going to dominate what's going on. Okay? So take a look here. So the limit as x approaches infinity of the pieces that have the highest degree, which would be the 2x squared and the x squared pieces, this would actually give me a limit of what? 2. And because the sign is bouncing up and down, I actually have a plus or a minus 2. It's going to be bouncing up and down between positive 2 and negative 2 because the sign is bouncing up and down between positive 1 and negative 1. Okay? So the coefficient being 2 on top and being the 1 on bottom gives me the 2. The plus or the minus is coming from the fact that sine goes between plus 1 and minus 1, and we're just multiplying them together. So it's almost like I'm doing, and let me write it this way, this might help. Some of you are looking at me weird. It's almost like I have this going on. The highest value sine goes as 1, the lowest value sine goes as negative 1. So when I take the 2 over 1, I still get it as plus or minus 1 as a multiplication factor here, so I get positive or negative 2. So this is sort of a problem. What can you tell me happens, that is, what is the limit if you're constantly bouncing up and down between positive 2 and negative 2? Well, the graph is doing something that is the graph of sine. Let me draw sine in here. Does this, right?
Right.
What's the limit as you go to the right? What value do you get close to? The x value is going to infinity. What value is a y's? Remember, limits are y values. What y value you're getting close to?
0?
Are you? Yeah.
Oh, I'm sorry. I read something wrong.
Okay.
You're getting close to negative 1 and 1.
Okay, for sine. Mm-hmm. So what does that tell you?
Those are your limits?
Does it?
Or is it that everything greater than 1?
The limit doesn't exist. It's not getting close to one specific value, right? Limits are supposed to be, in fact, what we've been talking about in this particular section is rational functions. So your limiting behavior is these asymptotes. This doesn't have an asymptote. It doesn't get close to positive 1 or negative 1. It just bounces up and down between them. It never gets actually close to any of them because the graph never stops, right? It's the wave that goes around the football arena forever. It never stops. It doesn't get closer to one particular person in the arena. It doesn't get closer to one particular place and stop. So this limit does not exist. But it does not exist not because it's infinity or negative infinity. Remember we talked about that at the very beginning of this lesson? That we could say that if a graph went up forever, its limit doesn't exist. But it's more helpful to say that the limit's infinity. Well, on this one, the limit doesn't exist, but not because it's infinity or negative infinity. It doesn't exist because it never stops going up and down. It never stops that pattern. Now, let me make one comment on this that would change the whole thing. Let's say that instead of it saying the limit as x goes to infinity of 2x squared sine x, it said 2x sine of x and x squared plus 4 on bottom. So all I did was take the squared off the x on top, right? Okay, so sine's still going to do the same thing, bouncing up and down between positive and negative 1. Agreed? So I'm still going to have that positive or negative 1 thing going on. But on this one, the highest degree of the exponent tells me the exponent on the top is 1, on the bottom is 2. What happens when we have a higher degree on bottom for asymptotes? What's my asymptote?
Zero.
No, it's 0, yeah. So if it were higher on top, it wouldn't exist. We wouldn't have one. But this one actually has a limiting behavior when I consider the x and the x squared of 0. Well, when I take 0 and I talk about 0 times plus or minus 1, does the plus or minus 1 matter? No, because I'm multiplying it by 0. So the reason that this happened on this one is because these exponents were the same. If the exponents had actually been smaller on top, then the fact that the exponent on top is smaller than the one on bottom would take into consideration. I'd still be bouncing up and down, but what would happen is that the waves would get smaller. Right? So it starts out large, going between 1 and negative 1, and then it tapers off, and we're still going up and down, but it's getting much, much smaller waves as we go. They're getting closer and closer to the x-axis. Yes?
So we got negative plus or minus 2, but you're saying the limit still does not exist for that, though?
Right, it doesn't, because the plus or minus 2 tells us the top and the bottom of where it goes. But it doesn't actually get close to either of those values at the end of the graph. It keeps going between them. Right?
So
It very much, it very much will look like this, but the peak and the valley, it won't be perfectly aligned to this. But the peaks and the valleys will be at 2 and negative 2 instead of 1 and negative 1, which is what they would be for sine.
So then on that example though,
This one down here,
would
the
your
new one.
limit be 0?
Your limit here would be 0, yes. Because what would change in terms of my graph is that I would have a graph that looked more like, I'll draw it on over here. And again, this isn't a perfect image, but it would look more and more like this.
As opposed to the other one, which has a constant.
Exactly.
Exact value.
Right, and we call it amplitude when we talk in trig, right? It has this amplitude where it always goes up and down between 2 and negative 2. This one tapers off. It's almost like what you're doing is you're trapping it, right? Instead of trapping it between 2 horizontal lines, you're trapping it between 2 diagonal lines. And those 2 diagonal lines tend towards the x-axis. That's the difference. Yes?
For back on problem number 4, you mentioned that it was only as x approaches positive infinity?
Yes.
How do we know that it's only approaching positive infinity versus negative?
Well, the graph, this question only asked us to find x goes to positive infinity.
Oh, is that just assumed when it doesn't say positive? on
Yes,
the
just like when you have the number 4, if it doesn't have a negative in front of it, we assume that it's a positive 4.
Okay,
Same
so
thing.
all 3 of these problems then are all
Yes.
assumed going to positive?
Yes, on this one, if the graph had gone to negative infinity, it would have looked like this. We would have had the negative there, but it didn't have that on this
Does
one.
that change anything?
It would. It wouldn't change the denominator because you're squaring a number and you're taking a square root. So it wouldn't change the denominator, but it would change the numerator because you'd be multiplying a negative times a negative number for x. So the numerator would actually become a positive value. So instead of it going towards negative 1, it would actually be going towards 1 on the end of the graph instead, because the numerator would be negative times a negative value. Yes, Tammy?
On number 5, like, whereas you have plus or minus 2, and then you have negative 1 to 1, but like, Which one are you looking at? Like, is for the,
Well, this piece of information, this piece of information right here was why we put this right here. The fact that sign goes between positive and negative 1 basically allows us to replace the sign value with the positive and the negative 1. That then tells us that there isn't a limit because it's going to be going up and down between 2 and negative 2. So this right here, my answer is that it does not exist. My answer is there is no limit here, and the reason is because this graph down here, again, this isn't a perfect image, but it is a sketch that's going to be fairly close to what's happening at the end of the graph, is the graph keeps going up between positive 2 and negative 2. A limit is a single value, or infinity, or negative infinity, that you're getting close to. Well, this doesn't get close to any single value. It keeps going up and down. It's not getting close to anything.
how does 0 change that?
Because 0 times anything is 0. Down here, when I multiply 0 times plus or minus 1, I get 0. Well, take a look at this graph. It's still bouncing up and down, but it's bouncing up and down much smaller each time, right? So the waves get smaller and they eventually level out at 0 if you were to go out far enough. That's the difference. This one over here, this picture, it doesn't level out. It bounces up and down with the same wave every single time. So I'm not actually leveling off. Whereas on this graph, I do level off. I am getting close to the x-axis as I go out towards infinity. That's the difference. And we see that happen in terms of the equation because the 2x over the x squared has a limiting end behavior of 0. And then 0 times the plus or minus 1 is still 0. All right.